Welcome to Math TV with Professor V. In this video, we're going to learn about chi-square procedures from Chapter 13 for Introductory Statistics. So starting off with Section 13.1, the chi-square distribution. The chi-square distribution is obtained from the values of n minus 1 times s squared divided by sigma squared. So remember, n, that's your sample size. S, that's your sample standard deviation, so S squared is sample variance, and then sigma squared is population variance. And this comes from random samples that are taken from a normally distributed population with variance sigma squared. You won't have to worry about computing any of this. But something to keep in mind if you're looking at how the chi-square distribution is obtained, n can't be negative, n minus 1, that's your sample size. And then you have your variance for your sample and population, which are both squared. So all of these values that chi-square takes on cannot be negative. That is the first big characteristic of the chi-square distribution. Second one is that the chi-square distribution is positively or right skewed. You can see that it trails off, right skewed distribution. So it's not symmetric like the normal and the t distribution that we've been working with a lot up until now. And much like the t distribution, the chi-square distribution is a family of curves based on the number of degrees of freedom. And at about 100 degrees of freedom, the chi-square distribution becomes somewhat normal. And just like we expect with most of our all of our probability distributions, right? The area under each chi-square distribution is equal to 1 or 100%. So in the past, with my students, I'd always give them a table. This table here gives you the degrees of freedom and then different levels here of significance. And these are all of the values that you would use to get your critical values when performing hypothesis tests and whatnot. So I'm going to do a couple examples by hand right now, but again, you're not going to have a table on the exam. You're not going to be doing anything by hand. I'll show you how to do everything that you need in StatCrunch. So let's just jump into 13.2, which covers the chi-square goodness of fit test. So there's different hypothesis tests that call for using the chi-square distribution or chi-square as your test value. The first one we're going to study is the goodness of fit test. And it's a statistical test that is used to test or determine whether a frequency distribution fits a specific pattern. Okay? And some of the assumptions that need to be satisfied first is that all of the frequencies, all of the observed values are 1 or greater. At most, 20% of the expected frequencies are less than 5, and that the data comes from a simple random sample. This might not make sense right now until we look at some examples, so don't worry. And then step 1, when you're performing a hypothesis test, the null hypothesis you typically write, the variable has, you don't say the specified distribution. You can sometimes, or you would actually write out what it is. It just depends. And then the alternative, sometimes you would see it say, yeah, the variable does not have the specified distribution, or H naught is not true, something like that. It's a little bit more vague. And then same thing, decide on the significance level. And then to compute the test value of the test statistic, the formula is as follows. So chi-square, this looks a little smushed. I like it here nice and spread out so you can understand. Remember this sigma, we've seen that before. That means sum or add up all of the observed, O is observed minus expected values. You square those and then divide by the expected value for each of the categories. What are the categories? You'll see. It's basically a frequency distribution that we're going to have. And then degrees of freedom is number of categories minus 1. Keep in mind the goodness of fit test is always right-tailed. And then all of the expected frequencies, the way you calculate them is you take the sample size n and then you multiply by p, which would be the relative frequency or probability assuming the null is true. All right, it might seem like a lot, but once we do a couple examples, it's going to be really straightforward. This is actually one of my favorite tests. I just like it. I like writing chi-square. It's a fun Greek letter to write. I like the test. I like how it works. Hopefully you enjoy it. Okay. So example 1, human blood is grouped into 4 types, A, B, AB, and O. The percent of Americans with each type are as follows. O, 43%, A, 40%, B, 12%, and AB, 5%. At a recent blood drive at a large university, the donors were classified as shown below. At alpha equals 0.05, is there sufficient evidence to conclude that the proportions differ from those stated above? And I forgot to give you your data table because it said the data is shown below and it's not there. So here it is. Oh, we'll do B and then AB. O, A, B, A, B. So this is at the blood drive. 60 people had type O blood. 65 had type A. 15 had type B, and 10 had type AB. This is what's observed. This is what we collected from the blood drive, okay? And let's just total them all up so we know what our sample size N is. So these will sum up to 150. Okay, so state the hypotheses and identify the claim. Basically, the null is what we are assuming the distribution of blood types is given this information here. So for H naught, I'm just going to say blood types are distributed as follows. O, 43%, A, 40%, B, 12%, and AB, 5%. My alternative hypothesis is just going to state that H naught is not true. I'm not going to specify which blood type doesn't fit that pattern because in order for H naught to be not true, only one of them or more than one could not match the distribution given. So we're not worried about how it differs. We're just going to say this is not true. And that's the claim, right? Is there sufficient evidence to conclude that the proportions differ? So that's what we're claiming, that H naught is not true, that the proportions differ from how it's stated here. All right, decide on the significance level. Well, they told me alpha equals 0.05. And then also notice there's 4 categories, 4 blood types. So degrees of freedom is going to be 4 minus 1, which is 3. And then next we have to compute the test value. So remember, test value formula chi-square is the sum of observed minus expected squared divided by expected. And I have all the observed values right here. So how do I get the expected? Well, I'm going to take all of the percentages that were given to me, right, in the assumed or believed distribution and compute it. So for example, our sample had 150 people in it, right? So if O is supposed to have or make up 43% of the blood types in our population, then you would take 0.43 times 150, and that gives us 64.5. So what I would expect is for 64.5 people to have type O blood in that sample of 150. A would be what was the percentage? 0.40, yes, times 150. So that's equal to 60. I would assume I would have 60 people with type A blood in that sample at the blood drive. B should be 0.12 times 150, which is 18. And then AB is, they can accept any blood type, right? 0.05 times 150, which is 7.5. All right, so those are all our expected. So now let's compute the test value. So we're going to have 4 terms added together. So for type O, observed is 60 minus expected 64.5. That's going to get squared. And then you divide by expected 64.5. And then continue. Plus, why plus? Because of this sigma. That means add them up. 65 minus 60 squared divided by 60 plus 15 minus 18 squared divided by 18 plus 10 minus 7.5 squared over 7.5. And then just do all this in your calculator. So, I mean, we're glad there's only 4 blood types, right? Otherwise, this would have been quite a bit of work. And you should get 2.064. All right, now we're going to find the critical value. So remember, our degrees of freedom were 3, and alpha was set at 0.05. So here I have pasted in good old table. Makes me nostalgic. So here's 3 degrees of freedom. Here's our alpha level, and this is right here my critical value, 7.815. Notice it already tells me here that the test is right-tailed. So critical value equals 7.815. Okay, so basically let's just orient ourselves. Where is everything going up? Oof. So here's my critical value, 7.815. To the right of it, this is always a right-tailed test. This is the critical region, also known as the rejection region. And now we're going to decide whether or not we reject the null. Well, here's my test value, 2.064. That's over here. That's in the non-critical region, non-rejection region. So that's what our decision is. We're going to fail to reject the null. So let's summarize the results now. So you would say there is not, because we failed to reject the null, sufficient evidence to support the claim that blood types are not distributed as listed above. I'm not going to list it again, okay? Another way you could kind of say it is, it can be concluded that the percentages are not significantly different from those given in H0. So look at kind of what we just did. Put some context on it. This is what we observed. And if these percentages were spot on, this is what we would have expected the distribution to be. And they are pretty close, right? That's basically what chi-square is doing. It's looking at how off everything is in proportion to each of the observations. So yeah, no reason to reject the null or say that this distribution isn't correct. Okay, one more example. A researcher wishes to see if the 5 ways being drinking caffeinated beverages, taking a nap, going for a walk, eating a sugary snack, or other, that people use to combat midday drowsiness are equally distributed among office workers. A sample of 60 office workers is selected and the following data are obtained. At alpha equals 0.10, can it be concluded that there is no preference? So here is the result of the survey, 60 office workers. So these are the observed. And then expected, think about it this way. They said twice. They want to see if the data is equally distributed and that there's no preference amongst these methods. So basically you would expect each of the methods to have the same frequency. If there's 60 office workers divided by 5, 60 divided by 5 is 12. So we would expect 12 to be in each of these. What do you do when you're drowsy? I chew gum. I do like taking naps, but like if I'm at the office, I don't think I would take a nap. I'm very curious what sort of office these people are napping at. Okay, so let's state the hypotheses and identify the claim. Null hypothesis is that there is no preference. Remember, the null always has to include equality, right? So there is no preference between the 5 methods. Right, there we go. And then the alternative, you can just say H naught is not true. Where's the claim? It's in the null this time because it's, asserting or claiming, can it be concluded that there is no preference? So claim is in the null. Okay, decide on the significance level. So they told me alpha is 0.10. This is a right-tailed test. And now we're going to compute the test value. So chi-square, sum of observed minus expected squared divided by expected. So first category, beverages, 21 minus 12 squared divided by 12. Yeah, that's a good one. I would get like a soda or a coffee maybe. 16 minus 12 squared. Who are these people napping? That's what I want to know. Plus, going for a walk, 10 minus 12 squared over 12. Plus 8 minus 12 squared over 12 plus 5 minus 12 squared over 12. Okay, add all of these up. You could just, if you're actually going to sit there and try to do this with your calculator, compute all of these differences and square them. And then at the very end, when you add them up, you can just divide by 12 once, right? Because in this case, the expecteds were all the same. And you should get 13.83. All right, now we're going to find the critical value. So degrees of freedom would be number of categories minus 1. There's 5 categories, 5 ways to combat drowsiness. Minus 1 is 4. Remember, alpha was 0.10. Let me go back to the table that was here. So this time we have 4 degrees of freedom, and alpha is 0.10. So here is my critical value, 7.779. Okay, so critical value 7.779. So let's think of it this way. Here's my chi-square distribution, right-tailed. Here's 7.779. This is the critical or rejection region. And where did our test value fall? 13.83, way out here. So as a result, we're going to reject the null, reject H naught, and now summarize. So we'll say there is sufficient evidence to reject the claim that there is no preference between the 5 methods to combat drowsiness. And I mean, you probably had a gut feeling that was the case if you just looked at the sample of 60 people, right? You're like, these don't look equally distributed. Come on. But it's not good enough to just say, like, I feel like it's not, right? That's why we have statistical tests. All right, so enough of doing stuff by hand. Let's get into StatCrunch so you can see how to crank these out, and we'll get p-values now this time too. Okay, so let's take a look at some of the homework from chapter 13. I'm going to start with this example here, question 6. A distribution and the observed frequencies of the values of a variable from a simple random sample of the population are provided below. Use the chi-square goodness of fit test to decide at the specified significance level whether the distribution of the variable differs from the given distribution. So determine the null and alternative hypotheses. Select the correct choice below. So notice here, this distribution, this is what we are expecting. Those are the expected values. That's what the null hypothesis is going to claim or assert that the distribution follows. So A makes no sense. B, no, it wouldn't differ. It would be the same as the given. So the distribution of the variable is the same, yes. And then the alternative would be that it differs. Okay. Remember, equality always for the null. Differs was in that alternative. Good. Then compute the value of the test statistic. So what we're going to do is open that data in StatCrunch. And then notice here, variable 1, the frequencies, these are observed. Okay, and variable 2, these are the expected. So you're going to go to stat, goodness of fit, chi-square test, observed. Observed, well, they were in, where were they? Which column? Observed were in, yeah, variable 1. And then expected is in variable 2. That's it. You just have to tell them where each one is. Compute. So here it gives us the value of the test statistic chi-square, 2.444. Since we're rounding to 3 decimal places, that's perfect for us. Okay, find the p-value. It's right there, 0.485, rounding to 3 decimal places again. So 0.485. Nice. And then we have to make our decision. So significance level was 0.05. And our p-value is much larger, 0.485. So that means we do not reject the null. There is not sufficient evidence. And that's pretty much it for that one. Okay. This one's super similar. There were a couple more I wanted to do for you. Yeah, this one. Let's redo this one. Okay, so a certain type of candy is reported to be distributed with the color percentages shown in the table below. The number of each color in a random bag of candy is also shown below. Use the chi-square goodness of fit test to decide whether the color distribution differs from the reported distribution. Use alpha equals 0.05. So determine the null and alternative hypotheses. Null is going to be the frequency is, no, not different from that reported. It's not saying it's the same for each color. It's the same as that reported. Okay. They really just write a bunch of garbage for the wrong ones. Next, compute the value of the test statistic. Okay. So again, let's open this in StatCrunch. And then here, percentage, that is what is expected. Frequency is observed. All right. Goodness of fit, chi-square test. Observed is the one that says frequency. Expected is the one that says percentage. Compute, please. So the test statistic chi-square is 9.989. Okay. And then the critical value. Ooh, so they're doing the traditional method. And notice here that StatCrunch did not give me the critical value. It gave me the p-value instead. So that's fine. To get the critical value, you can either look up on a table for your chi-square distribution where alpha is 0.05 and degrees of freedom is n-1, or we can just do it right here. So you go calculators, okay, chi-square, and chi-square test is always right tail. So change it so that x is greater than something. and alpha was set at 0.05. And then degrees of freedom is n minus 1. So number of categories minus 1. There's 1, 2, 3, 4, 5, 6 categories, 6 colors. So degrees of freedom is going to be 5. And hit enter. So this is the same value. This is my critical value that you would have gotten off of a table. All right, but we don't need to carry tables with us. And so the critical value is 11.070 if we're rounding to 3 decimal places. 11.070. Good job. So what's our decision here? Well, notice the test statistic is not in the critical region. 9.989, that's like right here. This is all the non-critical region, non-rejection region. So no, there is not sufficient evidence to reject the null. Good. And then I wanted to do one more, about the fair die. I thought this one was fun. So a researcher drilled a hole in a die and filled it with a lead weight and then proceeded to roll it 217 times. Wow. I mean, I hope someone helped them. I don't know how long that would take. Okay. The observed frequencies for the outcomes of 1, 2, 3, 4, 5, and 6 respectively are given there. Okay. How many times it landed? 1, 37. How many times it landed? 2, 28, etc. Use a 0.056 significance level to test the claim that the outcomes are not equally likely. Does it appear that the loaded die behaves differently than a fair die? Okay, so what's the null and alternative hypotheses? No one's talking about things being equal to 5, okay? All outcomes are equally likely, yes, because when you roll a fair die, all outcomes should be equally likely, right? 1 out of 6 chance. And then alternative, at least one of the probabilities is different. D has them reversed. That doesn't make sense. Remember, null always includes equality, either an equal sign or a statement involving equality. So that's the correct answer. Now we're going to compute the value of the test statistic. So here they just gave me observed, right? From rolling it 217 times. That's fine. What you're going to do is go stat, goodness of fit, chi-square test. Observed was in variable 2. I'm pretty sure. Let me double check. Yeah, variable 1 just tells you what the value of the die was. Nobody cares about that. And then expected, you're actually going to click all cells in equal proportion because that's what our null is. We're assuming that each value is equally likely, right, to occur. If you have a fair die, that's what it should be. Compute. So here we go. Compute the value of the test statistic. There it is, 6.38. This time you're only rounding to 2 decimal places. Read that carefully. I can't tell you how many times I thought I did something wrong, and it's just that I didn't round to the correct number of decimal places because they always switch it up on you. Okay. And then find the p-value. It's right there. 3 decimal places this time. Okay. 0.271. And does it appear that the loaded die behaves differently? So alpha, what's my significance level? Right here, 0.05. P-value 0.271, that's very large, greater than alpha. So that means we do not reject the null. So no, there is not sufficient evidence to reject the null hypothesis. Well done. So, and this goes back to when we studied probability. If you think about it in chapter 4, like just because you do have a fair die, in this case it was loaded, but there's no guarantee that when you roll it 217 times, you're going to get an equal number, right, of all of the possible outcomes. That's just how probability works. But it's close enough to being equally distributed that we don't say that this lead weight changed the outcomes, the likelihood of the outcomes. So that's it for chapter 13. Hope you guys are enjoying that chi-square test. I like it so much. I also like writing the chi-square letter symbol. Have fun. Stay tuned, you guys. Subscribe if you haven't already. Math TV with Professor V. And chapter 14, we're going to get into regression and correlation. Good stuff.